around you, at the everyday world with routine motion. All of it has a key component in physics, an essential piece of information that defines how a physical quantity manifests and interacts within space, and that is direction. When you're looking at a map, it guides you towards where you are going. Whether we are talking about the push of a wind current, or the velocity of falling raindrops, or even an entertaining piece of Parker, motion, lift, thrust, all of it depends not just on how much, but where to. So these are quantities that require more than just magnitude. Their definition requires direction. And in physics, we call such quantities vectors. And that is exactly what we shall be looking into today. In physics, vectors are visually represented using arrows. These arrows start at the tail and go up to the head. The length of the arrow shows the vector's magnitude, while the direction in which the arrow points indicates precisely where it's heading. So here you can see a vector drawn on a simple Cartesian plane, and we can measure its horizontal and vertical extents by projecting it onto the axis. One thing to take note of is that vectors aren't fixed to a specific point. So even if we shift the vector around, be it towards the right or move it upwards, or even swing it around in a full circle without changing its length or direction, it remains exactly the same vector. As long as the magnitude and direction are preserved, the vector is unchanged, no matter how we reposition it. Now let's take up an example to further understand the difference between scalars and vectors. So on the left we have a plot of wind velocity, and on the right one of temperature. So for wind velocity, it matters immensely the direction of the moving current, not just the magnitude. While in case of temperature, all it tells us is how hot or cold it is at some point. So this fundamental difference between scalar and vector quantities shapes the way we analyze physical phenomena and solve real-world problems. Let's now look at some special cases of vectors. First, we have equal vectors. So two vectors are said to be equal if they have the same magnitude and direction. Now, if one of the vectors is scaled up or down, then the two vectors still have the same direction but not necessarily the same magnitude. These are now parallel vectors. And if you scale one of the vectors by a negative factor, then the vectors point in exactly opposite directions. These are antiparallel vectors. And if an antiparallel vector also has the same length as the original vector, then it is called the negative of that vector. Adding a vector with its negative gives us the null vector, which has zero magnitude and no defined direction. It's represented as a point and plays the role of zero in vector addition. Finally, we have the case of unit vectors, and these have a magnitude of exactly 1. Unit vectors are used to specify direction in a given coordinate system. In 2 dimensions, we use I hat pointing along the x-axis and j hat pointing along the y-axis. As you can see, they form an orthogonal set and serve as the basis of 2D vector space. That is, any vector in the 2D plane can be constructed as a linear combination of these two vectors. Say we have a vector A drawn from the origin. We can break it into its horizontal component ax I hat and vertical component ay j hat by projecting them onto the x and y axis respectively. Together they sum up to form the original vector, and this is called the component form of the vector A. This idea holds for any vector in the 2D plane, as you can see here, and we can decompose any of these vectors in terms of I and j hat. In fact, this idea generalizes easily to 3D as well, something we'll look into later. Now, suppose we know the magnitude of a given vector A as well as the angle it makes with the positive x-axis. In such a case, we resolve the vector using trigonometry. The horizontal component is given as the absolute value of A times cos of theta, and the vertical component as absolute A times sine theta. So, if the magnitude of A is 4 and theta is 30 degrees, then we get x equals 4 cos 30, which is equal to 2 square root 3, and y is 4 sine 30 degrees, which is 2. And this gives us that vector A is equal to 2 root 3 I hat plus 2 j hat. This process of vector resolution is essential for working with inclined forces, motion on ramps, and nearly every physics problem that involves direction. Now let's try to understand how two vectors are added geometrically, starting with the triangle law of vector addition. We begin with two vectors on the Cartesian coordinate plane. So here's the first one, v1. It starts at the origin and points upward and towards the right. And the second vector, v2, also starts at the origin but points downwards and slightly to the right. To add these vectors using the triangle law, we shift v2 so that its tail meets the head of v1. The resultant vector, the sum, is the arrow drawn from the tail of v1 to the head of the shifted v2 vector. And this is represented by the red arrow here, v1 plus v2. But what exactly does adding vectors mean? Let's try to look at this from a different angle through the idea of displacement. Imagine the grid is covered in dots and each one represents a point in space. So first we apply the vector v1 to the entire space, that is, we shift every dot in the direction and magnitude of v1. This is like dragging the plane along that vector. Now we can do the same thing for the vector v2. This time we apply v2 to all the points. This cumulative effect is exactly what the resultant vector showed us before. And that is exactly what vector addition does. It models consecutive displacements. Let's visualize this even more clearly with just a single moving point. We start at the origin, we first move the point along v1, and then we continue from there along v2. Now compare that to a second point that takes a direct route, moving straight along the resultant vector v1 plus v2. Both points arrive at the same final destination, and this captures the essence of triangle law. Applying vectors one after the other is equivalent to the single direct displacement given by their sum. Now we can look at another equivalent method for vector addition, which is the parallelogram law. So once again we begin with two vectors v1 and v2 drawn from the origin. And to apply the parallelogram law, we need to construct a copy of v1 starting at the head of v2 and a copy of v2 starting at the head of v1. The lines we just drew are dashed version of those vectors, forming a complete parallelogram. The diagonal of the parallelogram starting from the origin gives us the result. And here that is the red arrow given as v1 plus v2. Actually, let's try to see how this actually works using the idea of components. So say we have v1 equals 2.5 I hat plus 1 j hat and v2 equals 1.1 I hat minus 1.8 I hat. So the resultant vector is given as v1 plus v2, which equals 3.5 I hat minus 0.8 j hat. In a similar fashion, we can explore vector subtraction as well. Say we wish to compute v1 minus v2. Now this is the same thing as adding v1 and negative v2, that is a vector with the same magnitude as v2 but pointing in the exact opposite direction. Now apply the parallelogram method. Place v1 and minus v2 tail to tail, construct the opposite sides and draw the resultant. This new red vector is v1 minus v2 and its component form is v1 minus v2 equals 1.4 I hat plus 2.8 j hat. You can do this using the triangle law of vector addition as well. You would simply take minus v2 and shift it so that its tail meets the head of v1, and the resultant vector can be obtained by connecting the tail of v1 to the head of minus v2. Now, what if we wish to find out the sum of more than two vectors? Let's explore that using the Polygon law of vector addition. Let's begin with 5 vectors a, b, c, d and e, and each of them start from the origin and have their own unique direction and magnitude. Now, in order to add them, we are going to place them head to tail, one after the other, starting with vector a. So one by one, we are going to take out each of these vectors and attach their tails to the head of the previous vector. Now, once we are done chaining all these vectors one after the other, all we are left to do is add a single vector, the resultant, from the tail of the first vector to the head of the last. And this red arrow is the sum of all 5 vectors represented by R over here. In fact, we can visualize the result as a sequence of intermediate sums. First we add a and b, and here's the resultant of that. Then we add that to c, and the resultant we get from that to d, and so on. And we can finally recover the full resultant vector. And thus we see that the Polygon law is nothing but repeated application of the triangle law extended to multiple vectors. Let's actually take an example to see how all of this plays into physics. So imagine a box resting on an inclined plane. Since it's at rest, this means that all the forces acting on it must cancel out. There are 3 forces at play here: the gravitational force mg, which acts vertically downwards, the normal force N, which acts perpendicular to the surface, and the frictional force mu N, which acts up the slope to prevent sliding. Now, to understand whether these forces balance, we can use a force polygon and draw each of these forces one by one, their tail to the head of the previous vector as we have done before. Now, if you see, the polygon closes, which means that the forces are in equilibrium, that is, the sum of n, mu n and mg is 0. The object thus remains at rest, and vector addition thus confirms that. Moving on, it's time to understand how vector addition works mathematically. So we have 2 vectors, a and b, and while vector a lies along the x-axis, b is inclined at an angle theta from it. Now let's suppose the resultant vector is given by c and that it is at an angle alpha from the first vector a. Now, how do we compute the magnitude of this vector c? Well, if we arrange these 3 vectors in the form of a triangle in the same order that we did when working out the triangle law for vector addition, we can resort to using the cosine rule. From the triangle thus formed, we can see that the inner angle c is equal to pi minus theta, and thus if we put this into the cosine rule, we would obtain that the magnitude of c is given as the square root of the modulus of a squared plus the modulus of b squared plus 2 times the modulus of a times modulus b times cos of theta. Now, to find the direction of vector c, it is sufficient to find the angle alpha which it makes with the vector a. So for that, we construct this triangle with sides c, b sin theta and a plus b cos theta, and thus we can see that tan of alpha can be given as the opposite, which is b sin theta, over the adjacent, which is a plus b cos theta. Of course, by A and B here, I mean the magnitude of the vectors A and B. Thus, we have found both the magnitude and the direction of the resultant vector C. We can now look at some special cases. So firstly, the case where theta equals 0 degrees. When the two vectors are collinear and point in the same direction, their magnitudes simply add up. That is, C equals A plus B. Now, if theta equals 90 degrees, that is, the vectors are perpendicular, then they form a right angle triangle, and the resultant in that case is the hypotenuse, so C equals square root of A squared plus B squared. Thirdly, when theta is 180 degrees, the vectors are collinear but they point in opposite directions, and the resultant is thus the difference of their magnitudes, that is A minus B. Now from all these three cases, we observe that the following inequality always holds, that absolute A minus absolute B is less than absolute C, which is less than absolute A plus absolute B. This gives us the possible range for the magnitude of the sum of the two vectors, and to see it, we can animate what happens to C as we gradually change the angle theta, while keeping the magnitudes of A and B fixed. This concludes our exploration of vector addition, both geometrically and algebraically. So for today we are going to stop here and continue in the next video. So make sure to subscribe to Eigen Akademie if you haven't already, and make sure to hit the bell icon so that you get notified each time I upload a new video. Thanks for watching and stay tuned.